And with that said, I'm just going to hand it over to our wonderful presenter, Steve Wetzel.
Thank you, Beth, and thank you all for joining us today. Hopefully, through this presentation, you will learn a little bit more about the role of VFD cable and what the story is. Is it essential? Is it required? Is it overkill and nobody needs it? Obviously, the truth probably lies somewhere in between, but let's get started and find out. So I'm going to start. If I can get my presentation going. There we go. I'm going to start with three quick stories to set the stage. And the first story is when things go well. Somebody buys a drive, they buy a motor, they buy the least expensive cable they can find, probably some single conductor THHN, and hook it all together, and everything works fine. This happens. This happens a lot. If it didn't happen a lot, the drive manufacturers would probably all be out of business. But sometimes things don't go so well. There was a pulp and paper mill in Canada that installed a new drive system. They were using standard cable and they had issues. They had motor problems. They had drive trips, drive failures. They had control and communication issues. They tried a variety of things to solve all these issues. They tried filters. They tried reactors. They tried chokes. Nothing was fixing the problem. Finally, as a last resort, they pulled out all our standard cable and they put in a VFD cable construction and it fixed everything. But the real interesting story is when things might go well, but then again, they might not. There was a steel mill in Indiana that was installing a new drive line. And so they went out to the major drive manufacturers. They weren't talking to the little guys, they were talking to the people that really know stuff about drives. And they got bids. And one of those manufacturers differentiated themselves from the others by saying, if you buy our systems, our drives, you don't need to use VFD cable. Well, they figured that into all the other information they had, and they eventually wound up awarding the business to that drive manufacturer, only to have them come back at the 11th hour and say, we've been thinking about it, and you probably really should install drive cable just to make sure things go smoothly. Well, if the drive manufacturers aren't sure of when we need to use drive cable or not, how can we be? But we have some guidelines that we can give you to give you a better idea. I was at a trade show, a factory automation trade show a while back, and I had a drive engineer from one of the major drive manufacturers come up to me, and he asked me if we made a VFD cable with PVC insulation. He told me he wasn't a fan. He's saying it was causing that construction was causing him all kinds of problems, and he wondered why would anybody make such a cable. Well, it's a really good question. There definitely is issues with using PVC insulated cables on drives, and we'll see what those issues are as we go forward. But why would somebody make such a cable? It's a very difficult question to answer. The answer is not obvious. If we look in the NEC, nothing is said about it there. If we go to the standards, UL, IEEE, ICEA, there's nothing there either. Why would anybody make such a cable? Well, you can find the answer. And that answer is found in the source of all knowledge, all electrical knowledge, which is the Bible. Judges 21:25 actually gives us the reason. And what it says in Judges is, in those days, there was no king in Israel. Everyone did what was right in his own eyes. Well, this was written 2,500 years ago. That's a good time before we ever had VFDs. So we need to take this verse and apply it for today's factory automation environment, right? And see how this verse can speak to us about the factory floor. So I've gone ahead and I've retranslated this verse to make it applicable for that situation. And what I came up with is, in those days, there was no VFD cable standard in America. Every manufacturer made what was right in his own eyes. And the fact is there's a lot of confusion about cable with drives because there is no VFD cable standard in America. Anybody can make literally anything they want and call it a VFD cable, including constructions with PVC insulation. There is no such thing as a VFD rated cable. But just last week, I was asked to supply one. Hey, we need to spec or we need to offer a VFD rated cable here. Well, there's no rating because there's no standard. Now we're working on fixing that. We're chairing, Southwire is chairing a working group on the ICEA, Insulated Cable Engineers Association, to create a VFD cable standard to help end this confusion. We have a few goals. We want to allow only specific constructions to be called VFD cable. We want to standardize the testing requirements and the minimum performance characteristics of this cable. Now, we are also in discussions with UL, and we will be with NEMA in the future, because everybody realizes this is a problem. We need to have a standard for this kind of cable. Well, why is this even an issue? Why are we even talking about cable? Certainly, there's more exciting things to talk about with drives and motors and PLCs and than cable, right? I mean, the cable is just a rope between the two, basically. But the reason is the wrong cable can cause a variety of problems. Literally everything on this list, to a greater or lesser extent, can be affected by the cable, and it all relates to decreased productivity. So it's very important to know if you need to use a VFD cable, but it's also very difficult to know because there's a lot of things to consider. Everything on this list plays a role, and everything on this list, or most of the things on this list, are very hard to quantify. How do you process all this information to help you make the best decision as to whether you need to use this cable or not? Well, once again, I'm coming to the rescue. Just like I retranslated that Bible verse, I've taken all this information and I've put it into an equation. And you simply turn the crank and you get an answer, and it tells you whether you need to use VFD cable or not. And if you believe that, I have a bridge in Brooklyn I'm looking to sell. So please contact me after the seminar. I will give you a really good price on it. Well, all joking aside, we obviously don't have a cut and dried formula like that. People want one, but all we can do is give guidelines. VFD cable is important if you use very long cable runs. Longer cable runs cause more problems. And you'll see why that's the case as we move forward in this presentation. If you're in an old buildings have less reliable ground grids, and that lack of a real solid ground grid can also cause problems. If your factory has sensitive control or communication systems, that can cause issues. If you run multiple drive cables in the same tray or conduit, that's an issue. If you just want to reduce drive trips in general, all these are good reasons to consider using VFD cable. Well, we looked at these issues. What's the cause of all these issues? Well, we're going to start with what it's not. And the cause is not 60 hertz power. Many people think of a drive as just varying this sine wave so that it's running a little faster or a little slower, but that's not what a drive does. A drive doesn't put out a single frequency waveform. What drives put out is this nasty looking pulse width modulated waveform. It's a lot of high frequency components in this waveform, and IEEE papers have told us that it contains frequencies up to and over 30 megahertz. So we're dealing with frequencies that are roughly 1,000,000 times higher than the 60 hertz coming out of the wall. So why would we expect it to work the same way? Well, why is high frequency a problem? Good question. And the reason is because things change at high frequency. Let's do a little cable engineering 101. We're going to look at this medium voltage cable. It's got a conductor. It's a single conductor cable. It's got a shield, insulation, a shield, and a jacket. And if we do an electrical schematic of this cable, we see that the conductor has a inductance and a resistance. And then parallel going down to ground, we have the capacitance of the cable, and we have the insulation resistance. Now, we want the resistance of the conductor to be low so we can push current down that cable very easily. And we want the resistive component of the capacitance, the capacitive reactance, to be high so we're not leaking a lot of current to ground. What we get is, if we do the calculations on this cable at 60 hertz, we get that. We get a very low AC resistance and a very high capacitive reactance. And electromagnetic interference, which is proportional to the current times the area of the loop times the frequency squared, well, we don't have enough information to really give a number on that yet. So I'm just going to use a unity value there. But now if we do those same calculations at only 10 megahertz, you can see everything changes. Our AC resistance of our conductor goes up by 178 times. our capacitive reactance goes down by over 163,000 times, and our EMI literally goes up by 1 million. Okay, everything is changing, and everything's changing in the wrong direction. Okay, big problems. So, what is a VFD cable and how does it overcome some of these issues? Well, the optimal VFD cable construction consists of an overall shield, a robust insulation, which we'll define later on, and a symmetrical 3+3 design. Now, of all the cable constructions I'm aware of out there, 100% of them have an overall shield. Less than 100% have a robust insulation, and even less have a symmetrical design. Why is this? Because there's no standard. So every manufacturer makes what's right in his own eyes. So let's examine each of these three components to see why they're so important. And we're going to start with the overall shield. And we're going to start very basic, and then we're going to move to some more complex topics as we go on. Excuse me. So let's start with just a drive, a motor, and an unshielded power cable. And look at EMI, or electromagnetic interference. Now, at high frequency, that unshielded cable acts as an antenna, and it broadcasts EMI throughout your facility. Now, EMI is proportional to the current times the area of the loop times the frequency squared, and we'll get into what the current and area are later, but that frequency squared, we've gone up 1 million from 60 hertz. So we've got huge increases in EMI. And what can happen is if that EMI affects a sensitive control or communication equipment, it can cause issues. They typically don't spontaneously combust, but they can have issues. They can hang, they can reboot, they can get fried, they can act in unexpected ways. There was a plant that put in a new drive system, and after they started up the new drive, they had a fire alarm. So they evacuated the building. They called the fire department. They went through the building and found no fire. So they were able to bring everybody back into the building. They started up manufacturing again. And when they started that drive line up again, they had a fire alarm. Okay. EMI can cause things to happen in unexpected ways. And EMI was causing this fire alarm to trip, causing a lot of decreased productivity until they were able to solve that problem. And so it's not always something that's sitting right next to the cable. It may be a significant distance away, and we'll see how that's possible as we go forward. But by simply shielding this cable, we reduce that EMI. By shielding, we're not allowing that EMI to affect things to nearly the extent that it could otherwise, and those devices can operate, and we can go on with a productive environment. Now, safety is another issue. Let's double the complexity of the diagram here to 2 drives, 2 motors, and 2 unshielded cables. And let's say that these cables were run in tray for a fair distance. And let's say we need to do some maintenance. So what we do is, obviously, for safety, we lock out and tag out. We bring in our electrician and we let him go to work. And what can happen is you can get enough coupling of the locked out cable from the energized circuit nearby to cause a potentially dangerous or fatal situation. This is documented in an IEEE paper. The bottom paragraph says if these 2 motor circuits travel together considerable distance in tray, for example, the open circuit may receive enough electromagnetic electrostatic coupling from the energized circuits to produce a driving voltage and current flow that could be dangerous or potentially fatal. So we obviously want to avoid that situation, and we can do that by using shielded cable. Because just like the EMI example, when we lock out and tag out and bring our electrician in to do work, you mitigate that coupling of the cables so he can work safely, go home at night to his family and watch Netflix or do whatever he does at home. Another issue that the shield takes care of for us is common mode current. Common mode current is defined as the sum of all currents flowing in the cable. So if we add up the phase currents, if we add up any ground currents that exist, any shield currents that exist, we want this to be 0 or close to 0, or we can have issues. Now with traditional power, this typically isn't a problem because we have this wonderful trigonometric formula, 3 sine waves, 120 degrees out of phase, equal amplitude, all sum to be 0. That's why three-phase power is the thing it is today, is partly because of this equation. This is my favorite equation that I learned when I was going to the University of Wisconsin in Madison for electrical engineering. And it plays a big role in what we're looking at today as far as seeing why we have issues. Now, typically, ground currents are 0. Shield currents are 0. In low voltage cables, we don't even have any shields. So my second favorite equation comes into play now, which I think I learned my junior year at Wisconsin. That was 0 plus 0 plus 0 equals 0. So our common mode current is adding up to be 0 with a traditional power system. That's why traditional power works really, really well. But in a VFD system, we have some issues because the phase currents do not sum to be 0. This trigonometric equation does not apply. We get these nasty pulse width modulated waveforms, which sum up to be who knows what. We'll look at ground currents later and shield currents later. But what does this look like? Well, if we take one of those phases and we overlay the sum, we get some big spikes. And the sum of those phases is pretty large. One drive manufacturer told me that they had measured 100 amps of common mode current flowing in some systems. So it's significant. Now, why is common mode current a problem? Well, we've increased our diagram, made it a little more complex here, right? We're back down to one drive and one motor. We've got an unshielded cable in there, and now we have an I-beam and a ground grid. So we're adding complexity all the time here. But what happens is this common mode current gets pushed down the cable from the drive to the motor. Now, it's got to return back to the drive per Kirchhoff's law. We can't have a non-zero sum of current at any node. So somehow that current has got to make its way back, but how is it going to get back? Well, it's high frequency, so it doesn't like to travel through tiny little ground wires. It likes to travel through large surface areas, like building steel. That's due to something called the skin effect, where at high frequency, current sees a lower resistance path by traveling on the surface area of a conductor as opposed through its cross-sectional area. So building steel, lots of surface area, very attractive path for this common mode current. So what's a large surface area path back to that drive? Well, it could go through the motor frame and base plate and then through building steel back to the drive. Now, we know that 100 amps has been measured in some cases. So what happens if that 100 amps is flowing next to the ground grid of some sensitive controller communication equipment? It can have issues, right? That can cause problems. Now, we really don't know where this path is going to be. It's uncontrolled. It's going to be different in every facility. It might go all the way back to the input transformer and then back to the drive. There's another path possible too, right? We usually hook up machines to our motors, and if we do that, we can have the path going through the motor bearings, shaft, through big factory machine, then back to through building steel back to the drive. And if this happens, we can have motor issues, including motor failure. Now, if the current goes through the motor bearings, shaft, and connected machinery, it flows in packets as that common mode. There's a common mode voltage also that's developed, and that discharges across the bearings, and it causes something called bearing fluting, which gives you repetitive ridges in the bearing race. You can see the picture here. Now, this fluting causes excessive motor noise, vibration, and failure. It's not uncommon for failure to occur 3 to 12 months after system startup. So you can be having this issue developing, and you don't even know it's happening for a long, long time. Now, an inverter duty motor does not solve this problem. Inverter duty motors were created in the 90s, I believe, to address the issue of standing waves or reflected waves. It was an over voltage that you get, and we'll talk about that going forward here in the future. But you're increasing the voltage that the windings see, and the windings were shorting out. So inverter duty motors were created which have increased insulation thickness on the windings, but they do nothing to deal with the common mode current. They only handle that extra voltage. You can use shaft grounding rings or brushes because those can divert the common mode current so it doesn't flow through the bearings, but they're not optimal solutions because they only protect the motor bearings. The common mode current is still flowing uncontrolled and can cause other issues in your facility. Okay, installing a shaft grounding ring or a brush is akin to taking aspirin for a brain tumor, right? It makes your head feel better, but the underlying problem is still there, and it will be until you deal with it. So you can see here's our messy diagram that we've had, and we have to make it more messy because we also have to talk about EMI in this case. And what happens is you can now start to see the area of the loop that we have here, right? We've got several different loops. It may go back to the input transformer. It may go through the motor frame and base plate or through the big factory machine and on back, but you can see the loop can be very, very large. The current can be very, very large. So we can have a lot of EMI generated in this situation. Well, what can we do? We can install a properly terminated VFD cable. What this does is that the goal is to create a low impedance path at high frequency for that common mode current to return back to the drive. Now, the way we do this is we use large surface area terminations of the shield at both ends of the cable. Some of the drive manufacturers call this a 360-degree termination. Again, the reason is 360 degrees. That's probably going to be a lot of surface area if you terminate that. You also want to terminate both ends of the cable because you want to create that path. If you only terminate one end of the cable, current won't flow through the other end of the shield, and we're not going to get that return path. Do not use pigtails. Do not use drain wires. They increase the impedance of that path. Use VFD termination kits or VFD cable glands. And this is an area where we can help. We have several different solutions. We have cable glands for all of our cable. We have termination kits if you're running cable in conduit and can't use a gland. We have training videos on how to install these things. We have application notes. We spend a lot of effort, a lot of time talking about these things because they're so important. What we have learned from direct contact with people in the field is many electricians only terminate one end of the cable. Well, if you do that, you are protecting against radiated EMI, but you're not controlling the path of that common mode current. So you're really throwing away a lot of the benefit that cable can give you. We've seen some electricians that don't terminate either end of the shield. Then you're not getting any benefit from that shield. So it's very important, and we're trying to make it as easy as possible to terminate these cables correctly. Because if you terminate these cables correctly, then we control the path of that common mode current. What we're going to do is it gets pushed down again, right, from the drive through the cable to the motor, and we're going to send the bulk of it back through that cable shield. The shield is large surface area. It's typically a short path, which also decreases the impedance of that path. And we're going to try and minimize the currents flowing in all those uncontrolled paths, right? Current flows everywhere. We just want to send the bulk of it back through the path of least resistance, which would be the cable shield in this case. This will shrink our EMI loop because the current and the area multiplier, I guess the current area product here will be very small because we're sending less of the current through this big loop, and we're sending more of the current through the shield, which is creating a very, very small loop. So benefits all the way around. Oh, conduit alert. I almost forgot. We have to talk about conduit. Conduit's really not a good solution for VFD cables because it's installed as mechanical protection, not electrical protection. Some people think I'll take some THHN, I'll put it in pipe, and I've got a poor man's VFD cable. Well, it doesn't do the job. It doesn't provide a safe path for that common mode current. It's not insulated. So where that conduit contacts building steel, that can be a jumping off point for that common mode current, and it's now flowing uncontrolled again. In addition, it doesn't allow for the symmetrical lay of the conductors and grounds inside the cable, which is our next point. So let's look at that next. Symmetrical design cables. Now, symmetrically designed cables have an advantage over a standard 4-conductor cable construction, and it accomplishes this advantage by using the cancellation effects on the ground currents. Remember my favorite equation? Well, let's take a look and see how it applies in this case. And we're going to start with a 4-conductor cable. Now, this four conductor cable, we have three phases and we have a ground, a green ground in this case, and each phase is going to induce a current on that ground. The blue phase and the yellow phase will induce currents that are equal amplitude and 120 degrees out of phase. They're equal amplitude because they're equal distance apart. Now, the red phase conductor will also induce a current on that ground, but it'll be lower amplitude because it's further away. It's still going to be 120 degrees out of phase. So when we add up these three waveforms, we get a non-zero result flowing on our ground wire. With symmetrical cable, it's a little bit complex, but the results are quite different. Let's take a look and see what these all sum up to. And we're gonna do it by breaking things down because it makes it real simple to see. So let's take a look clockwise. We're going to see what the phase conductor induces as far as the ground conductor clockwise to it. And if you see, we're all equal distant away. They're 120 degrees out of phase. So we're going to get three current flows on those ground conductors that are equal amplitude, 120 degrees out of phase, and that adds up to be zero. Now, if we look counterclockwise, we get the same thing basically, right? Equal amplitude, 120 degrees out of phase, adds up to be zero. We got one more way, and we look opposite. Well, it's further distant, so they're all lower amplitude, but they're still equal, still 120 degrees out of phase and zero. And my second favorite equation, once again, comes into play, right? 0 plus 0 plus 0 equals 0. So symmetrical cables reduce the amount of common mode current generated. They reduce that current component flowing on the grounds, and they also reduce your cable bend radius because a 3-conductor cable is 11% smaller diameter than a 4-conductor cable, so you can fit it in a little bit tighter place. In summary, we can reduce the common mode current effects by either controlling its path with shielded cable or by minimizing its generation in the first place by using symmetrical cable. Electromagnetic coupling. This is another issue where symmetry can play a role. And one of the drive manufacturers told me they had a situation with a customer. He had non-shielded conductors he was using, just standard old THHN. He had multiple drives and motors, and he put all the cables in one tray. And he had a rather random cable layout. So he had 5 circuits here. And you can see that the cables are not grouped by circuits. They were just thrown in this tray pretty much haphazardly. And what was happening was he was getting drive trips. Now, I don't think his drives were tripping exactly like that. I think they were just stopping to operate. But, you know, how do you show stopping operation on a PowerPoint presentation? My goodness. Well, what's the cause of this? It's electromagnetic coupling. What happens is if we look at the center conductor here, the brown phase of circuit 3, it couples with the conductors next to it, and it exerts a current and voltage on both those conductors. And it does this further out too, right? It just has less of an effect as we get further away. But it's not just the number 3 brown that's doing this. It's also the number 2 yellow. And it's this conductor over here and that one over there. And we're getting a lot of confusion as far as currents and voltages induced because of this coupling. And what happens is the drive gets confused. So since the drive is confused, it just shuts itself down. And now you've got to wait for the drive to be able to be restarted again. What's the fix? Well, this application engineer had, this is what he told the customer. Go back and group all the cables by circuit. So now we've got circuit 1 together, 2, 3, 4, and 5 together. And he suggested going through and secure them all with cable ties. So now this is a lot of labor, right? This takes a lot of time to secure all these cables together. It takes a lot of time to move them in the tray as well. So I think it's really a good thing that the customer saved some money up front on the cable, buying less expensive cable, so he had more money to pay for all this labor. But there's a better solution, and that's fix number 2, and simply install VFD cable. VFD cable has this unique feature called auto grouping of your conductors, right? You're never going to have the issue where things aren't grouped together. So you're getting these cancellation effects. And in addition, you get a free shield, which even furthers the cancellation of electromagnetic coupling. Now let's talk about insulation. And before we talk about conductor or cable insulation, we need to look at the voltages that we're going to be dealing with. What voltage is this system going to produce, this VFD system? Well, standing waves are an issue. Remember we talked about inverter duty motors? Standing waves are an issue with drives. They're caused by the high frequency pulse width modulated waveforms. In theory, the voltage doubles, but in practice, it can be even higher. I think it was Yogi Berra that said, in theory, theory and practice are the same, but in practice, they're not. And that's the case here. Now, and as I mentioned with inverter duty motors, this was what was causing motor winding failure. That's why those motors were created. Now, what's the actual voltages we're talking about? Well, according to IEEE papers, it's 2 to 2.4 times the DC link voltage of the drive. That's up to 1,560 volts peak on a 480 volt drive system, almost 2,000 volts peak on a 575 volt drive system. And those peaks are hit at the carrier frequency of the drive. So 3 to 12 kilohertz, that's how often you're hitting those peaks with your smaller drives. Now, these standing waves are functions of many things. They're a function of the impedance mismatch between the motor and the cable, of the power transistor rise time, and of the cable length. So we're just going to look at power transistor rise time and cable length in this diagram because the impedance mismatch is relatively constant. But if we look at old gate turnoff thyristor technology, we had rise times in the order of 4 microseconds. And so we had very long cable runs that we could use. We didn't start to see here's the vertical, here is our motor over voltage. I max out at the theoretical doubling. And then horizontally here we have cable length. We didn't start to see any issues until we're running over 300 feet of cable, and we didn't max out on a full reflection to over 3,000 feet of cable. Well, who's running those kind of cable lengths in their factories? Almost nobody. But over time, we used faster power transistors inside our drives so that today, with the IGBTs that are used, those are insulated gate bipolar transistors. They're in pretty much every drive, every low voltage drive from every drive manufacturer. The technology is all the same. So this presentation applies regardless of whose drive you're using because they're all using IGBTs today. And we start to see a reflection in those drives with a cable length of 4 feet. Now it's not much, but we max out with that reflection at about 35 feet of cable. So it's a completely different situation than it was back in the days when we were using slower power transistors. Fortunately, the solution is very, very obvious of how to deal with this problem. We just need to build really, really small factories. Keep your cable lengths below 4 feet, and this will never be an issue for you. And if you cannot do that, then we just need to use cables that can handle these standing wave voltages. Now, cable voltage ratings are specified in RMS volts, and a 600 volt rated cable is designed to handle, hope you can stick with me here, okay, 600 volts. That's the RMS value of that sine wave. Now, that sine wave has a peak voltage, which we multiply by the square root of 2 to get that, and that is 850 volts. And we hit those peaks every 120 hertz. Now let's put everything together, a 40 volt system and a 600 volt cable. RMS, it's really simple, right? A 480 volt drive system runs at 480 volts RMS. A 600 volt cable is rated at 600 volts RMS. I think I was a sophomore at Wisconsin when I learned that the 600 volt cable rating is higher than the 480 volt drive rating. So cable rating is higher than the system voltage. That's good. We're good to go. RMS of the pulse width modulated waveforms, not going to do it. Okay, we're going to move on. Peak voltages. Well, we just take the square root of 2 to get the peak voltage of an RMS sine wave. So the 40 volts times the square root of 2 gives us 679 volts peak of the system. The cable has an 850 volt peak rating. 850 volt cable rating is higher than the 679 volt peak of the drive rating. We're good to go. If we look at this from a pulse width modulated, from a drive output waveform peak voltage, well, we saw that IEEE paper tells us that those peaks can be 1560 volts for a 40 volt drive system. Our cable rating still is 850 volts, so we are significantly exceeding that voltage, much higher than the cable rating. So can you use 600 volt rated cable? Depends who you ask. If you ask the National Electric Code, yes, they don't have anything much to say else about it. If you look at another document by the National Fire Protection Agency, NFPA 79, the machine builder standard, they say you can, but they have restrictions. Let's take a look at those restrictions. This is a paragraph from NFPA 79. Electrical conductors and equipment supplied by power conversion equipment as part of adjustable speed drive systems and servo drive systems shall be listed flexible motor supply cable marked type RHH, RHW, RHW2, XHH, XHHW, or XHHW2, or selected based on the equipment manufacturer's recommendations. One cable, one low voltage cable is missing from this list, and it's THHN. Why is that? Well, some people say it's because THHN is a 600 volt cable. And that is true, it is. But XHH, XHHW2 are also 600 volt. Actually, all these cables can have a 600 volt rating. So it's not just the voltage rating is the reason for it. So why not THHN? There's a lot of reasons. And we're going to look at each one very briefly. We've already looked at electromagnetic coupling from the point of view of drive trips, and it's laid haphazardly in tray can cause some real issues. But let's move on to insulation compound, because if we go back to our graph, there's one big difference between THHN and all the other insulations that are listed, all the other insulations that are called out by NFPA 79. The allowed insulation types, cable types, are all thermoset insulations. You use either XLPE or EPR in general for those cables. Only THHN is PVC insulation or thermoplastic insulation. Well, what's the problem there? Well, thermoplastic compounds will soften, flow, and distort when you subject them to heat and pressure. The way we make these cables is we heat up the compound, we extrude it and melt it, we extrude it over the conductor, and then we cool it, and we're done. That insulation can be remelted when exposed to heat. Take a torch and try it sometime if you want to. Thermoset compounds, however, are different. They do not soften, flow, or distort when subject to heat or pressure. The way we make these cables is we heat up and melt the compound, we extrude it over a conductor, and then we cure it or vulcanize it. And a chemical change takes place, so those compounds cannot be remelted when exposed to heat. For thermoplastic compounds, I like to think of popsicles, okay? Go to the grocery store, buy some popsicles, go back to work, leave them in your car all afternoon, and see what you have when you come out. You no longer have popsicles, right? You've got some nice sugar water there. But thermoset compounds are more like cookies. And if I take a batch of my wife's chocolate chip cookies and put them in my car when I go to work, and it sits out in the hot sun all day long, and I come back, those cookies have not melted. And in fact, they actually taste better because they're warmer. So thermoset compounds are more robust. They're not as easy to damage or cause issues with. Now, another issue is the thickness of that insulation. And if we look at the average minimum wall thickness of THHN, we start with a number 14 conductor of 15 mils only. And at a number 6, we're up to 30 mils of insulation. XHHW, 600 volt XHHW, same voltage rating, twice the insulation thickness at the smaller sizes. Not only is it a more physically robust insulation, it's also twice as thick in the smaller sizes. And these both relate to some degree to corona inception voltage, which is the voltage at which corona discharge starts to occur within your insulation. Now, when this happens, it causes heat. It'll cause melting of a thermoplastic compound. You get ozone, and eventually you get failure. It's the beginning of the end for the cable. Now, if here's our corona inception voltage, every voltage below that does not cause this damage, this discharge. But voltages above the corona inception voltage will cause damage. So what happens is in 600 volt THHN, we can have a corona inception voltage that is lower than the reflected waves that cable is going to see. So every time you can see the red highlights there, every time my waveform turns red, I'm causing a corona discharge, I'm causing damage in that insulation. Now, 600 volt XHHW, which is the next thinnest insulation that we have, the corona inception voltage is much higher, so this does not happen. Another issue is wet withstand voltage, which is how much the cable can handle before it sees a fault. Now, this varies by compound, and if we look at dry versus wet withstand, well, both XLP and PVC, if they're both whatever their withstand is, and XLP is actually higher. This graph is misleading from that point of view, but when they get wet, XLP loses 5% of its withstand rating. That's nothing compared to the 55% THHN can lose. Cold flow is another reason that THHN cables are not good for drive applications. We've already seen we can have some problems with the insulation from it being thin, from it exceeding the corona inception voltage just with the normal thicknesses. But with THHN, it can do something called cold flow, where you can distort, move that insulation at room temperatures when it's exposed to force. Well, what kind of force? And this doesn't happen with cross-linked insulations, but maybe pulling it around a bend of a conduit. So we've got a conduit, we put a cable inside it, and as we pull that cable in, we can thin that wall, which causes only more problems. Finally, cables are capacitors. And this is the formula for capacitance. Capacitance equals 7.36 for a single shielded conductor. E, where epsilon is the dielectric constant of the insulation. Small d is the diameter of the conductor, big D is the diameter over the insulation. Now, if you think about it, thinner insulations are going to give us a smaller d over d. So smaller number on the bottom, that's going to increase our capacitance, right? THHN has the highest dielectric constant of any insulation we have. Higher epsilon is going to give us a higher capacitance. It also has the thinnest insulation we have. So thinner insulation, higher capacitance. THHN is the highest capacitance cable we have. Well, why is this an issue? Well, for most applications, it's not. Most applications are just dealing with 60 hertz power, right? Here, if we've got some 60 hertz power and we've got a cable with a high capacitance hooked up to a motor, at low frequency, capacitors don't leak a lot of current at low frequency. We get a little bit of leakage current, but most of the current goes down to the motor and everything works just fine. But with drives, things change, right? We're dealing with these high frequency waveforms. And at high frequency, we leak a lot more current to ground. Remember that medium voltage cable schematic I showed early on? We increased our capacitive reactance by 160 some thousand times. You're leaking a lot more current to ground in those situations, and that can cause drive trips or even drive failures. Now, THHN, all things else being equal, THHN can have 10 times the capacitance of a drive cable. This is why that drive engineer had a problem with PVC insulated drive cables. He was seeing these exact problems. And his customer was telling him, but I bought a VFD rated cable, right? That's why we need a standard. How do we fix this? Well, if you've already got an installation, and especially if you're dealing with a fractional horsepower motor, what you can do is buy a bigger drive. And this is often a solution that's proposed by the drive manufacturers. Buy a bigger drive. Now we just send more current down that cable. We still leak a ton to ground, but we get enough down to the motor that everything works okay. But if that's cost prohibitive, I know it's an expensive option, or if you're just dealing with this upfront, sizing it upfront, buy a better cable that doesn't leak as much current to ground so enough current gets down to the motor to have things operate. Cable installation, installations for VFD applications, THHN has issues with single conductors. With grouping the conductors, you minimize that electromagnetic coupling. NFPA 79 compliant, THHN is not. Corona inception voltage, you can literally be damaging your insulation with the reflected waves that occur. Wet withstand, if you're in a wet or humid environment, all the more reason to use VFD cable. Cold flow can happen to thin the wall and cable capacitance. For VFDs, we recommend using a thermoset insulated cable for all inverter to motor cables. Voltage rating should be 600 volts or higher. I know according to my graph, we can have close to 1500 volts that we're seeing, but 600 volt rated thermoset insulated cables can handle that voltage just fine, and they're allowed by the code. Now, there are other solutions out, and I should just say THHN is really a good product for building wire applications. We're a firm believer in it. We make a bunch of THHN and sell it for those applications. Just don't use it for your VFD applications. It's not the right cable. Now, there's other solutions out there, and some people say, well, maybe I should get something else instead of a cable. But in general, they're more complementary than competitive. Load reactors or DVDT filters, for instance, they can fix some of the issues that cables can fix, but other issues like capacitance and EMI, well, a cable is going to give you much better reduction of those problems than you're ever going to get by using a load reactor or load filter. There's a company called Hammond Power Solutions, and they sell some of this stuff, but even on their website, they state that VFD cable is better at solving these problems than the filters or reactors. Now, there's something called a sine wave filter, and they can mitigate many of the issues at in systems where you're using very, very long cable runs. And this is something the VFD cable cannot do, but they're very expensive and bulky. And if you don't match them properly, you can have increased problems. However, if you're running very, very long runs of cable, you may need to use something like this with an older motor so you don't short out the windings. In general, VFD cables really do a good job of reducing your EMI and controlling common mode currents. But VFD cables do nothing to reduce the reflected wave magnitude, and they do nothing to reduce harmonics. You need other devices if you need solutions for that. And also remember, more devices always requires more room to install and more time to maintain. You're going to have the cable regardless. So start with the cable, and if you have other issues that need to be addressed, there are other devices to address those issues. Now, there are several different cable constructions that exist, and these are our data sheets, but we have the three major types of VFD cable shields and construction, so we'll go over them quickly. First is the copper tape shield. And this cable is a 2000 volt rated cross-linked insulation available in a variety of sizes. Now, note up here, we do say PVC in the data sheet, but that is for the jacket if you read the construction callouts. If we look at insulation, it's cross-linked polyethylene type RHH. So insulation is where you want your thermoset materials. A PVC jackets are just for mechanical protection. They're perfectly fine. Also, we have a continuously corrugated welded aluminum armored cable with symmetrical design, rated everywhere from 600 to 8,000 volts. So if you have medium voltage drives, this can be a solution for that. Also cross-linked insulation, and this can also be used in Class 1 Div 1 environments. In addition, we have a copper braid aluminum foil construction. It's not symmetrical. It's a standard construction in the industry with 4 conductors, a drain wire. It has both 600 and 1,000 volts ratings. It's cross-linked. It's cost-effective, but really only in the smaller sizes because you're paying for extra copper you don't need in terms of the full-size ground in here and the full-size drain wire. It's a popular construction, but I always say beware because this drain wire just tempts electricians to terminate the shield with the drain wire. So I don't like the construction from that point of view unless you really are on top of your installers to make sure that they use the proper terminations when installing this cable. Now, somebody is going to object and say VFD cables cost more. And there's no denying that a VFD cable will cost more than a non-VFD cable, just like buying a VFD costs more than not buying the VFD and just running 60 hertz power, right? But if that's all there was to the story, nobody would use a VFD. The reason people buy VFDs is they spend money up front on that VFD to save money down the road. So invest in the right cable and terminations up front to save money down the road. If you can eliminate one drive trip, you have paid for that cable. Chances are you're going to eliminate more than just one issue like that. And the cable pays for itself just as the drive does. The cost to not install VFD cable can easily exceed the cost to use it. So use it. We make it very easy for you to access our VFD cable specs. If you go to industrial.southwire.com, click on the magnifying glass, type in the 3 letters VFD, and hit return. All of our VFD cables and accessories will show up. And click on any one of those, and you can go directly to its information. We also make it very easy to access our application notes in a similar manner. Go to industrial.southwire.com, click on the tech blog menu item, type in again VFD in the search, hit return, and all of our VFD app notes come up. We also have a cable calculator, VFD cable calculator. You enter in your pertinent information, and it provides your properly sized VFD cable, gives you all the information that you need. In summary, the best VFD cables have 3 features: an overall shield, which reduces EMI, improves safety, and controls common mode current; a symmetrical design, which reduces common mode current, allows for tighter bends, and minimizes electromagnetic coupling; and a cross-linked insulation to meet the requirements of NFPA 79, handle reflected voltages, and reduce capacitance. Beware, there is no such thing as a VFD rated cable because there is no standard. We're working to fix that, but you need to do more than just say you want a VFD rated cable if you want to ensure you get the best solution for your system. VFD cable constructions vary, so we suggest buying from a knowledgeable manufacturer. Proper shield termination is essential for optimal performance. If you do not terminate both ends of the shield properly, you have wasted a lot of money in buying that cable to begin with. We have a lot of expertise in factory automation and VFD applications specifically, and we would love to help you optimize your VFD system performance. So if there's anything that we can do, please contact us. We're more than happy to help. And finally, take care in specifying VFD cables, or you could end up with a PVC insulated cable. Thank you very much. Beth, I will turn it back over to you. If you have any questions, please send them to factoryautomation@southwire.com. Have a good day.
All right. Thank you, Steve. That was incredible information. Very, very thorough. If anyone wants to if anyone wants to ask a question, if you'll just send that to us in the chat. We've got about 9 minutes left if anybody wants to do that. And while we're waiting for that, oh, there we go. Just got a question come through. All right. So does the amount of copper in the grounds matter, Steve?
It doesn't really make a big difference, because where you really want that copper is you want the large surface area connection. Remember, IEEE papers have shown that common mode current will flow through large building infrastructures, large surface area building infrastructure. So if it's going to flow through steel, the cross-sectional area of your ground conductor doesn't really mean a whole lot. It's just flowing on the surface. So the grounds, while every little bit helps, I don't think you're getting enough return for the investment there. It's better to do a good low impedance at high frequency termination of that shield to force that common mode current back through the shield, because it doesn't like to flow back through the ground conductors.
All right. Thank you, Steve. All right, I don't see any other questions. We've got 5 more minutes if you'll hurriedly send me your question. But other than that, I wanted to let you guys know that we're going to be back on Thursday. We've got a class, Plan and Execute Successful Feeder Wire Pulls. Johnny Sellers and Bill Fowler are presenting that class. It's give you some tips and tricks on how to make every wire pull successful. And then Sai Shaheen's going to be back, that first one's at 11. At 2 o'clock, then Sai Shaheen's going to be doing a repeat of copper versus aluminum. If you want to tune into that, that's going to be awesome. And we have lots of different classes for you. I'm going to go ahead and put our link in here. So if you want to go to our website, all you have to do, it's so simple to re-register, or you don't have to re-register, but what you're going to do is you're going to modify your registration. So just go to that link I just put in the chat window, and you can just, at the very top of that page, just click register now, or actually you can click already registered and the system will go ahead and pre-populate your information, then click submit and you'll see all the classes listed down there for you to register for the future. So we'd love for you to join us. And I don't see any questions. Does anybody else have any questions that were sent to you privately, either Jay or Yushin or Brad? Does anybody have anything else? All right, then. I'm going to go ahead and give you 3 minutes back on your day, and we appreciate y'all being here today. Thank you for Steve, Jay, Yushin. Thank you for being here today, and we'll see everybody next time. Thanks for coming. All right. Bye-bye.